And on that note, we would like to wrap this presentation up.
Now moving on, we will have the last presentation of session 3. So the presenter is Mr. Rune Hendriksen, professor of the Technical University of Denmark, and he will be talking about new technology for AMR surveillance. Professor is currently working at the Technical University of Denmark, and also he is an external advisor in the Europe CDC, and he has served as a various advisory roles. So please welcome him with a big hand.
Yeah, so thank you for inviting me. It's a great pleasure to be here and talk about some of the topics that I like most, which is AMR and whole genome sequencing. So basically, my talk is more about the perspectives in the direction that I believe that we are moving. And I think that I would start with a quote, as also Professor Park started with, from Maggie Chan. And I'm not talking about how dangerous AMR is. I think we all know that. But I think that it's important to stress her last line about the need of a harmonized and standardized approach for surveillance in a One Health context. I think this is really the goal that we are trying to achieve. So we already have a lot of surveillance systems in place. These are built on phenotypic data. We have, as also Park mentioned, national surveillance, we have regional surveillance, and we have global surveillance. But again, when we look more into the data, the question is how reliable they are. So again, we have the surveillance in order to take action. But if we take the wrong action, set up control and prevention mechanisms based on faulty or incorrect data, then it doesn't really matter anything. So this is just some examples of our ECRA trial that we did last year here in Southeast Asia in relation to the UK 8 Fleming Fund ECRASIA project. So this is the data from 15 public health laboratories in this region testing into cocci. And as you can see, 2/3 of the labs have actually deviations above 5%, and some of them actually up to 30%, which is a bit scary when you think about that this is surveillance data, but it's also the labs that actually provide data for treatment. So if 1 or if 3 out of 10 tests is incorrect, then there might be other solutions to this. So that was already thought into the surveillance regime more than 10 years ago. So I think it all started with the launch of the first Illumina benchtop instruments and the launch of the Global Microbial Identifier. So you might not have heard about the Global Microbial Identifier. There's actually a meeting going on right now in Vancouver in Canada. But it started with a meeting in 2011 in the EU Commission, where DTU, along with the US CDC and the US FDA, had a talk about how can we move a genomic-based surveillance forward. And here it was visioned that at that time, that in 5 to 10 years, we would actually have sequence instruments in most of clinical labs, and that the cost of a bacterial genome would be about €50 or $1, and that we would have the capacity to share data across borders in databases and being able to do jointly cluster analysis. That was kind of the vision back in 2011. So basically the concept of that was to move from single isolates with whole genome sequencing and then allow us with bioinformatic tools to identify species, resistant genes, virulence factors, and also cluster analysis. And that would enable us to detect emerging resistance, clones, in a faster pace than we do with phenotypic methodologies. So I was supposed to talk about new technologies, But I'm sad to say that the new technologies is already a decade old. So I think that nothing have really emerged since the benchtop whole genome sequence instrument. So I did a bit of timeline here where we can see that in 2010 there was the launch of the HiSeq, and more or less at the same time there was also the launch of the MiSeq, which is a more medium level platform. And this was also at the same time when we had the GMI meeting in Brussels. And then, of course, there have been releases more or less every year, but again, it have not been major developments. So I just put in a few, so the NextSeq replacing HiSeq, and then NovoSeq, which is being used for really bulk analysis and more metagenomics. But we shouldn't forget also the ONT that there was a bit of a hype around in around 2010-11, and then finally it was marketed in 15. And that's opposed to Illumina, a long read technology. And that has actually some promising features that I will also touch upon. So what is also important when we talk about a genomic-based surveillance is, of course, cost. So it was envisioned that the cost would be like €50 already in 2011. So this is just an example of current cost. This is example from 19, and in one of the columns we have Public Health England, and basically at that time in 2019, the cost including also labor was about 125 euros. I think that was a bit conservative. I would think that we can actually generate a genome for less than 50 euro today, and with staff cost, it would probably be around 100. So we are not that way off with our vision back in 11. So what is new is not sequence platforms, but it's more applications and tools. So I did a few years ago, also in 2019, along with the US FDA, a bit of a review on what sequence tools or bioinformatic tools are available for predicting AMR. Since this is a meeting about AMR, I just list all of them. So I identified at that point 47 tools that can in silico predict resistance. So the question is how useful this is. And we really need to benchmark these tools, and not only now, but also in the future, because that's where the new technology lies. That is with new application, new tools. So we definitely need to ensure that with the launch of new tools, that these are proper benchmarked, because otherwise novel users would have no clue if they can actually trust the outcome. Because what is difficult in a whole genome sequence-based surveillance is not to generate the genome, it's to actually analyze the data, because as also Dr. Shawar showed, that suddenly you have 1 million genes, and what does they mean? How do they confer resistance? And I also saw pictures or illustrations from Professor Park showing a number of genes, and basically a lot of people already have problems with determine what confer resistance to what. So it's not, I see it not every day, but weekly, that for instance TEM1, people think that this is a resistant gene conferring resistance to third generation cephalosporins. No, it's just ampicillin. Then all the oxa genes, it's a mess. Oxa10, they believe that that is a carbapenem resistance. No, it's also just plain penicillin. So again, whole genome sequence-based surveillance open up a completely novel area of understanding data. And on top of the resistant genes, we also have the mobile elements. So we talked about usage yesterday. And usage is definitely a driver, but there's also other drivers. There's sanitation, there's infrastructure, but there's also the contribution of transmission and mobile elements. So we shouldn't forget about mobile elements, because that is probably also an area that we need to pay attention to. So if you use a drug in the human sector, it can easily, even if it's not used in the animal sector, cause resistance in the primary production of animal and food. But anyway, all of these tools are useful. I have marked some in red that we have benchmarked, that we always tell people that they can trust. But some of these tools that you would find would either be commercially available in black boxes. They might also be open access. Some would take a lot of time to compute, others just a few minutes. Some would be lab-based, web-based, with open access. Others would be command line and pose a lot of complexities to the end users. But this is where we are. So where the problem also arises is still with the repositories. So when we generate data, what do we do with all this data? So we try to store them locally, but there's also a tendency that institutions, governments, regions do not really want to share these data because suddenly they can be used for more than just the surveillance. So basically there's a tendency that we do not want to share data. I have listed here a number of surveillance programs that in one way or the other try to collect data and share it. But again, I still think that we are in its infancy. It's not really open access, even if those that develop these repository tell others that this is open access. No, it's not completely open access. It is with limited use. So I have experience with the ECDC platform EpiPulse, where you can see some data, but you cannot see all data. It's the same with Genome Tracker in the US. Again, some data is not shared. So I want to at least highlight a few examples here. So what I like is the FDA system with the Salmonella Resistome Tracker. I actually think that gives quite a nice feedback in terms of what data that are in the repository. It also allows for cluster analysis. Opposed to that, and I'm not saying that this is wrong, the other example is a European system where it's more a closed system where data are shared between organizations. So again, these systems all comes in different shapes with multiple purposes, etc. But it's not for all, and it's not completely transparent and open access, in my opinion. So as I indicated, that what I think is a nice system for now is what we have with the EpiPulse from ECDC. And again, it's not completely open access, but at least here, this is where we in Europe, where I have my best knowledge, is where we are able to share our Salmonella data and E. coli data and so forth, the genomes and the metadata. And there would be weekly alerts that be afraid of this emerging clone that have caused an outbreak of that, and so on. So at least we are going in the right directions. But again, I think this is an area that is also one of the limitations, along with a million other limitations to move this really forward. But at least, even if we have limitations and challenges, we should of course not be afraid of moving this forward. We have to ignore that there would be some intermediate difficulties, but if we don't push the boundaries, we would actually never end with the final result, which in my opinion should be a global whole genome sequence-based surveillance. I think that has so great potential that we need to overcome some of the barriers. So we have also tried with a UK aid Fleming Fund program to set up surveillance in also Africa. So for those that do not know about the Fleming Fund, it's a grant of 235 million British pounds that it goes to low and middle income countries in Asia and in Africa. And it's managed by the UK government, And we have just ceased the first phase from 19 to 21, and now moving into the second phase of the program, where there's allocated 210 million British pounds. But anyway, in this system, there are some regional grants. One of those are a sequence grant in Africa. So there's multiple players in Africa trying to set up surveillance. So this is just one of them. It has a funding envelope around 6 million British pounds. And the term of reference was to establish free whole genome sequence regional sites in East, West, and Southern Africa, and then within 3 years to sequence about 15,000 bacterial genome and do multiple training courses. And basically, we succeeded with doing that. We set up sequencing sites in South Africa, in Tanzania, Ghana, and expanding to Senegal, and but also pulling out from Nigeria, where we also had. So we ended up with 6 sites and are reducing now because of the funding envelope to only 3 sites. That was the term of reference. But we actually, in that period, succeeded to sequence around 20,000 bacterial genome and SARS-CoV-2. And we are also moving into setting up central sites, and I'm coming back to that. So basically, within these 3-4 years, we actually were able to establish some sort of surveillance in Africa. I know that this is not a full-blown surveillance system, but again, it's a proof of concept. It shows that it is actually doable to do this, to both collect the isolates, sequence it, and make sense of it and policy making. So what we want to do is take it to the next level, and that is to democratizing sequencing. So basically, when we have established a surveillance system with a referral system, we also want to see if what we collect centrally is also what we would see in frontline diagnostics. So again, the beauty of the long-read sequencing with MinION is actually that it's portable. So you can actually move it to the frontline clinics, you can move it into outbreak areas, etc. So that was what we also trained along with FAO recently in Ghana, where we hosted some training courses. And here, with the technology, we are able to multiplex up to 12 bacterial isolates on one flow cell and run it, and then being able to do the downstream analysis from a software that operates offline, meaning that you can actually take this laptop software, bring it to the field, do the analysis in the field, and then bring back your data, or when you have internet, to upload it and send it back to central analysis as well. So this is maybe where we see the future, and that is to do also a more centralized surveillance rather than have everything done in a reference center locally in each of the countries. So basically, what I think is novel in this area are the portable part of it with sequencing. So basically, this is just one example with the bento labs, that you can actually put a lab in your backpack, go to a site, and you do actually your DNA purification. You use your MinION, and then you actually sequence there. If you have internet access, you can also upload your data and do more in-depth analysis more locally. So that's one direction. The other one is that ONT have a tendency to produce gadgets, I will call it like that. So this is also just a bit of a disclaimer, but we discussed that a bit with Johns Hopkins University that have a bit of experience with these gadgets. So ONT have the idea of marketing in low batches new versions of MinION. And be cautious, they do not work as always. So it is maybe a bit of a fail and trial strategy. So again, now they try to market the Trax iron. I have heard, that's my personal opinion, that it doesn't really meet the benefits. But anyway, as I said, we have to move forward. So this is not a complaint, it's just a reality that there will be new platforms being marketed that might not work as intended, but anyway, we need to move forward all the time to make platforms better, faster, and more reliable, and at the same time try to build the needed infrastructure. So what is also nice with the MinIron is, of course, also, as Dr. Shawar talked about, that you can actually use it to close plasmids. So Shawar talked about closing plasmids with PacBio, but actually you can also close plasmids, which is also where we're going in the future with surveillance. And that is actually to do hybrid assemblies with Illumina and MinIron, and then actually being able to trace and investigate further the entire plasmids, as there have been several examples of in this conference as well. So moving a bit into another area of metagenomics. So I'll come back a bit to some of the examples of metagenomics, but before that, I just want to mention as well that when we talk about new technologies, we also need to mention the high-C sequencing. So again, this is a high-throughput genomic methodology that also embrace epigenomics. And basically, the idea of it is to build a more 3D genomic concept. And that, I think, has promising features. And that would probably close some of the limitations and gaps that we see when we do shotgun metagenomics in virus, where we can't tell really variants apart. They would be mixed up. And it would probably also close the gap that we have in AMR. So I have seen multiple examples of shotgun metagenomic studies. I've even been part of it myself. But there is a problem to link the AMR genes with the plasmid, with the bacteria. That is still one of the limitations. So even if we see very nice pictures and it gives some nice results, it needs still to be interpreted a bit with care. I think that high-C sequencing might actually close that gap in the future. I don't think it's just around the corner because everything is expensive, but this might be something that we should pay a bit more attention to. So there is a number of barriers, and I think that's really maybe why we haven't seen a lot of countries implementing whole genome sequence-based surveillance. Because as I said, we started 10 years ago, so why didn't it really happen? It didn't happen in Europe as well. So right now, we are modernizing with ECDC, the public health laboratories in EU with their diagnostics. So they are at the same level as in Africa, basically. And as also Ernesto talked about yesterday in the veterinary and food area, we were in the forefront maybe 5 years ago, but there was no funding in actually equipping all of the national reference laboratories for the food and the veterinary area, and because of that we are falling back. And in our surveillance in Europe, it's only the specific surveillance of ESBL, AMC, and carbapemesis where there's allowed to use whole genome sequencing. The rest is still based on phenotypic testing. So we need to address these barriers. And I've just listed a few here that we definitely need the in-country buy-in. So governments need to acknowledge that this is a powerful tool and this is going to be the future. And we need the funding to make sure that we have established the IT infrastructure and the equipment in place. We need to ensure that there is a straightforward procurement procedures and there are reliable supply chains. I think Jeff can talk about all the problems about that when we try to procure ONT for Africa. There's a lack of isolates. So not all countries actually save isolates. They would collect them, and after testing, they would just discard them. So we need to save these, at least if we want to do single isolate sequencing. Then there's the trust and sharing of data, which is also one of the limitations of really moving forward. Staff retention. Especially in low and middle income countries, every time we educate and train a bioinformatician, the day after they have a job in the US or in Europe. Then there's the knowledge and training and education. Many countries do not have bioinformatic training or education. That is also needed. And then there's, of course, the IT infrastructure that we really need to invest in. So if we don't have this in place, we would never have a genomic surveillance-based genomic surveillance-based AMR surveillance. Anyway, I talked about metagenomics. So that is likely the next step, but personally I also think that it's a bit out in the future. I have seen multiple researchers talking about the global surveillance based on wastewater, on feces, field runoff. We even in DTU collected waste from airplanes in light of trying to do proof of concept of AMR surveillance. And I'm not saying that this is in vain. This is actually moving the technology forward, but we not just need to make sure that we interpret the data in care, and that maybe is not always the case. So I just have some examples here of a very fancy analysis I was part of myself, where we collected sewage from around the world. And again, we just need to make sure that when we set up something like that, that we think about what samples is it actually that we collect. So here we collected samples from wastewater treatment plants from industrial countries and compared with grab samples from developed countries, which would likely represent Mr. and Mrs. Smith and their dog, but it doesn't maybe represent the entire populations as the wastewater from industrial countries. At the same time, it's also a problem, as I indicated, to really piece everything together. But at least it gives indications, and I think that this is a great tool to be used as a screening process. So if you see signals in studies like that, you definitely need to act on it, and that might actually be to collect cultures and do more single isolate sequencing to follow up on that. So I'm not saying that this is not the future. I'm saying that this might lay a bit ahead of time, and it serve as a good way of picking up signals. So metagenomics is what we would call the new black. So it's really a hype. Everybody is talking about metagenomics, but we also need to bear in mind that when we talk about metagenomics, there's shotgun metagenomics and there's 16S metagenomics. And 16S metagenomics is a great tool to identify different species. So it has served a great purpose in COVID surveillance in wastewater, and it can also serve as a great purpose for identifying bacteria. But again, be careful when you want to piece again stuff together with bacteria, plasmids, AMR genes. It is more difficult than anticipated. You need a sufficient sequence depth and coverage. That might actually be covered by the high-C sequencing in the future. And then there's all around understanding the data. So this is not as trivial as it is with phenotypic data, where I think it's a bit more easy. Here we need to understand what it all means when we talk about mobile elements, resistant genes, and so on. And then when we look at these abundance profiles, we need to make sure that we also understand, so what do the cutoff means? So when do we see disease? When should we be cautious? And when is it just something that goes below the radar? So there needs to be much more research into this to set cutoffs so we know what actually we see. And then the problem is also cost. I think that metagenomic is about 2,000 US for one sample, so this is not cheap. So coming to an end, I think that in the last decade, we have seen a lot of whole genome sequencing moving into research and diagnostic. So again, new technologies, I think it's been there for quite some time, but at least we're moving into field and central site sequencing. I think it's a great opportunity and alternative to phenotypic suitability testing, as also Dr. Shawar talked about, that this has already been proven by research, and there's already enough studies showing the high concordance. There's a great added value in sequencing, so even if the cost is 100 euros or dollars, it would be less than if you do all the analysis with conventional microbiology. That would actually probably cost more with pulse field, plasmid screening, etc. And then we need to build the national capacities. It's been in academia for the last decade, but in national reference laboratory, it just started. And then we shouldn't be afraid of the risk of short-term challenges. We need to overcome them. We need to invest in that, because that will be the future. And I'm certain that we need a bit more political investment and buy-in if we need to be prepared for the next pandemic, which would probably be with the use of whole genome sequencing, maybe with metagenomics. And I think I'll end here, so thank you again.
네, 감사드립니다. 그 질문하실
So thank you very much. Do you have any questions? We will take some questions from the floor.
좀 마이크 좀
Thank you for your wonderful presentation. It was very impressive. It's not a question, it's a kind of comment. I don't know your background exactly, but I was very impressed. And international organizations like WHO or FAO should recognize what you have done and what you're looking for. In the future, how can we manage the MR all over the world correctly? So I think the international organization should collaborate and develop the kinds of future technique to disseminate all the member countries to develop and to find out how can we control AMR correctly. So thank you again, and in the future I hope that all the international organizations and each country may join your wonderful idea. Thank you.
Thank you, Professor Park. And I just want to acknowledge that both WHO, FAO, and WOHA are working along in these initiatives. So we are all well aware of it. I think that it probably need a bit more political buy-in from countries themselves, because again, I acknowledge that these health organizations do not have a ton of money to invest in this. So we all need to bring money to the table and the commitment, and then we might actually move somewhere. But it might be a good idea to bring it up in health assemblies. So I know WHO have their assembly, FAO have their, and again, as we had the resolution text, as you also quoted from 15 with Margaret Chan, we maybe need something around this as well to be prepared for the next pandemic using whole genome sequencing. So I think there's a need for the recognition of the power in the technology rather than the support, because it's already there. But thank you, Professor Park, for the comment.
예, 혹시나 추가적인 질문
Any other questions from the floor? If not, I have a question for you. So in our department of microbiology, microorganisms, well, when we isolate the pathogenic bacteria or germs, we analyze them and we do serotyping and we analyze against antibiotic agents, and we are building up a database. Now afterwards, in the future, the NGS technology will become more common, and we are building up a WGS related DB as well. Now, at the government level, I don't know, we have some issues because we're working on two separate databases and we have limited budget. So ultimately, where should we focus more on? Which is the database that will end in the future? So we have DB on genotype and phenotypes, and we have research on the correlation between the two. And so in your opinion, where should we focus on? If maybe we can just choose one database and work on that, that might be better for us. So what do you think?
Very good question. So first of all, those that are moving into or replacing phenotypic surveillance and moving into genomics, there's probably a need, if they are accredited, to run the technology in parallel, and there's an ISO standard describing how to do that. So there needs to be an intermediate period of overlap to show that the concordance between it, unless that you trust the data that have already been shown, for instance, by the US FDA. In terms of databases, you're not the only one. I think that it's rare to hear some countries having only one database. So basically, even in Denmark, we have three institutions, one dealing with animals, the other one food, and then public health. They have separate databases, and that is because, again, the fear of sharing all data. So basically in Denmark, we have these three databases with joint interfaces, and that means that all of the three institutions can assess the genomes from all and do cluster analysis, and they would also be able to assess minimum data, metadata such as the species, the date, location, and source, and so on. But when it comes to privacy data, then it's the separate databases. So that's where they don't have access to each other. So I think it's good to have a joint database if you can convince all in Korea to have just one center, also to save money. I think that's recommendable. But again, it's more often to see that there are multiple databases in one country, despite of that.
네, 감사합니다. 예.
Yes, thank you very much.
좋은 발표를 해주신
So once again, I would like to thank the professor for your great presentation, and we'll wrap up this session here.